In this video we're going to talk about perspective projection, which makes objects appear on the screen with realistic proportions, like railroad tracks extending straight to the horizon and coming together into a single point somewhere away from the observer. The same object will appear larger when it's close to the camera, and then it becomes smaller as it moves away from us. On slide number 10, 3D transformations, we have a link to opengltutorial.org, and this tutorial has a very nice demo, the projection matrix, which shows objects in camera space before the projection transformation and what it becomes after the projection transformation. Okay, so our next slide is number 21, perspective projection. I will open this in a new image tab for our discussion. So what we're discussing here is that our objects that we placed in the world space and then transformed into the camera space now appear to be in camera space or in camera system of coordinates. So what it means is that the eye or the camera is now located at the origin of the system of coordinates, and we're looking down the negative direction of z-axis. So the viewing volume here is shaped like a pyramid or a rectangular cone, and it's the same system of coordinates now showing the origin of the system of coordinates right here, right? So this is the same idea. This is what we call field of view, measured as an angle along the y-coordinate, and we have two planes, one that we specify as the near plane on the z-axis, and another one is the far plane, also on z-axis, and all objects that appear in front of the near plane or behind the far plane will be culled, will be removed from the view. Also, objects that are partially fit into this volume of view will also be partially clipped. Okay, so only portions of these objects will become visible. Right here on this graphic we have our objects shown in this camera space, and obviously this is our viewing frustum. In this graphic we have blue objects shown in camera space, and the red pyramid-like shape represents the viewing volume, also known as viewing frustum of the camera, which includes the scene that camera can actually see. So clearly this position right here, the origin of the system coordinates, we can figure it out by simply continuing these sides of the pyramid. So this is the origin of the system coordinates right here. Just like scaling, rotation, and translation, we can construct a projection matrix, and multiplying coordinates of our objects by the projection matrix has this effect. Red pyramid has become a perfect cube, and the blue objects becoming stretched. When we are constructing our projection matrix, we can specify the field of view, this angle, 5 degrees or 40 degrees or 60 degrees. Then we specify location of the near plane, which can be like 1 unit away from the camera or 2 units away from the camera, depending on our modeling proportions. And the far plane could be located maybe 100 or thousands or 5,000 units away. This is really our choice, how we define this frustum of view, this pyramid. But then, as we multiply everything by the projection matrix, this cube, which is called OpenGM view volume, now has the coordinates of everything between -1 and 1 on all sides. Okay, so this entire cube is fitting into coordinates between -1 and 1. And this projection transformation is like warping the space, so that obviously you see that the blue objects that are located closer to the camera, like in this view, our camera or our observer would be located right in front of this plane over there, right? So that plane of the cube, and the observer is here and they're looking down this way. Whereas originally it's shown us standing here at the origin of the system coordinate and looking down this way. So this is our camera and we're looking this way. So many of these blue objects are outside of the view volume, and so therefore, of course, they will be culled and not shown. The blue objects in front of the observer are still stretched, creating the impression of the perspective, and of course any parts that would be further away anywhere outside of viewing volume would also be clipped away. Alright, so this is what it looks like when we look through our camera and seeing this behind the frustum. Of course, objects in front of the camera appear larger and others are smaller, creating this realistic real-life view. And still we have the proportions of our frustum or view volume in range from -1 to 1 and from -1 to 1 on both x and y axis of this projection. And finally, the last mathematical transformation is applied to fit this to the actual window size, and this is our pixel resolution of the screen, like here for instance 1024 by 768. So that would be the final operation, and this image will be finally rendered on the screen.